In the previous set of videos, we were talking about algebraic expressions, and of course the point there was to change to equivalent expressions that would always be true for all values of x. Now we're starting basic equation solving, and because we've learned a few important rules for changing algebraic expression to equivalent expressions, this will help us in basic equation solving. So this is a very introductory video. If you're good at algebra, you probably don't need to watch this video. In solving equations, the variable has either a single unknown value or a couple unknown values, and the point is to find what the variable equals. So this is a very different game from the game of simply rearranging algebraic expressions. Here we're actually trying to find the value for the variable. We need to solve for x, which means isolating x, that is, getting it by itself on one side of the equation. The basic mathematical constraint is that whatever we do to one side of the equation, we have to do to the other. In other words, we can add the same thing to both sides, we can subtract the same thing from both sides, we can multiply or divide. Whatever we do to one side, whatever mathematical operation, we have to do that same mathematical operation to the other side. Mathematically, we are allowed to do many things, but strategically, there are very specific steps in solving any problem. These steps involve undoing the order of operations. So it's very important to have this distinction of what is mathematically allowed, that's a broad field of possibilities, versus strategically what are the best steps to solve the problem. So suppose we have to solve this simple equation, 3x plus 5 equals 17. Theoretically, it should not be a big challenge to solve an equation like this, but let's talk about this. First of all, mathematically, there are many things we could do. For example, it would be mathematically correct, say, to add 40 to both sides of the equation. Now, there'd be no reason to do that, but there'd be nothing in the laws of mathematics saying that that was a wrong thing to do. It would not be mathematically wrong. It would simply be strategically wrong. Just because we could do something does not mean it is the most strategic thing to do. There are many more things that we could do than are strategic to do. It's very important to keep that in mind. So what would be strategic? Think about the order of operations acting on x. First we multiply the x by 3, then we add 5 to the product. That's the order we need to undo. We begin by undoing the plus 5 by subtracting 5. What we do to one side, we must do to the other. So we subtract 5 from both sides of the equation. 3x plus 5 minus 5, the 5's cancel on the left side, and on the right side, 17 minus 5 is 12. Now we have to undo the multiply by 3, so we divide by 3. And of course, when we divide both sides by 3, we get x equals 4. That's the answer. Now here's the same equation. Notice that we could begin by dividing both sides by 3. That would be mathematically allowed. Strategically, that would not be the smartest move. You see, if we divide it by 3, every single piece, the 3x, the 5, and the 17, all would get divided by 3. And so we'd wind up with this fraction equation. That would not be the best thing. So it's really good to subtract before we divide. Now, why is that? Strategically, it's always important to think about the order of operations acting on x and follow those steps backwards. So what's going on here? Why backwards? Think about it this way. When you put on footwear, the order is you put on your socks, then your shoes. Of course, when you remove footwear, you don't remove items in the same order. You have to take off the shoes first, then the socks. Undoing changes the order, both in footwear and in many other articles of clothing, and in mathematical operations. So it's just like shoes and socks. Whatever goes on first comes off last. So here are a few practice problems. Pause the video and try these on your own. And here are the answers. And of course, in each case, what we did was we added or subtracted, got rid of the constant on the same side as the x before we divided. What if x appears on both sides of the equation? Suppose we have something like this. Here, our initial strategy is to get all the terms involving x on one side and all the constants on the other side. So here we're going to begin by adding 3x to both sides. So on the On the right side, the x's will just cancel, and on the left side, we get 2x plus 3x equals 5x. Now that we have everything on both, we have all the x's on one side, now we can just add 7 to both sides. We get 5x equals 23, and divide. We can express the answer either as an improper fraction or a mixed numeral or a decimal, depending on what the answer was looking for. Here are some more practice problems. Pause the video and try these. And here are the answers. Everything we have covered in this module has been linear equations, that is, equations in which the highest power of x is 1. The rules become very different when we're no longer dealing with linear equations, but everything I've said here is true for linear equations. So in solving equations, our goal is to find the unknown value of the variable. Mathematically, it's always legal to do any arithmetic operation to both sides of the equation. Strategically, we undo the order of operations to isolate the variable. And if the variable appears on both sides, we begin by collecting all terms with the variable on one side. Eliminating fractions. This lesson concerns linear equations with fractions involved in the coefficients and the constants. I'm assuming that you are already familiar with the content of the fraction lessons in the Arithmetic and Fractions module. And if you're really not very comfortable with fractions, I'd strongly suggest going back and watching all those videos. They give a thorough treatment of all the operations involving fractions, all the basic rules of fractions there. Here I'm just going to do kind of a brief review of a couple key facts. So fact number 1, the product of any fraction and its reciprocal is 1. This means that if a variable is multiplied by a fraction, we can undo this by multiplying by the fraction's reciprocal. So that's really important. If we want to isolate x, and x is times a fraction, all we have to do is multiply by the reciprocal. Fraction fact number 2, this one doesn't really have a name, but the basic idea is that if you think about order of operations, multiplication and division are at the same level of priority. We can multiply and divide in any order. Now, I'll add the caveat, everything in the numerator has to stay in the numerator, everything in the denominator has to stay in the denominator. If we start multiplying by something we were dividing by, that's a problem. But if we just are multiplying and dividing, for example here, we could multiply a times b and then later divide that by c. Or we could start out by dividing b times c and multiplying a by that quotient. Or we could start by divide a by c and then multiply b times that quotient. And so we can rearrange into all these forms, and all of these are mathematically equivalent. That's very important. In particular, this means that we can think of a variable in the numerator of a fraction as a variable times a fraction coefficient. So 3x over 5 is identical to 3/5 x. Those are not two different things. Mathematically, they are identical. And that's very important to realize. So for example, if we had a very simple equation such as this, well, of course, that 3x over 5, we're going to rewrite that as 3/5 times x. Now we have a fraction times x, and we're going to multiply this by its reciprocal. X equals 5/3 times 2/7, multiplying through, we get 10 over 21. This equation simply involved multiplication. Things get a bit trickier when addition or subtraction of fractions is involved. Another equation with fractions. So here we have 7x over 6 plus 2/3 equals 15/2. Well, here we will begin by clearing the fractions. You see, we have addition or subtraction, and that makes it a little trickier, but one easy way to clear the fractions is to multiply by the least common multiple of all the denominators. Here the denominators are 6, 3, and 2. Those are the three denominators, and the least common multiple of those is 6. So we will multiply every term by 6. So, of course, 7x over 6 times 6, the 6's cancel, we just get 7x. 2/3 of 6 is 4. And 13 halves times 6, well, the 2's cancel, and we're left with 13 times 3, which is 39. And of course, once we get it into this form with the fractions cleared, then it's a very easy equation. We subtract 4, we get 7x equals 35, then we divide by 7, and we're left with x equals 5. Here's another example. For this one, we have denominators 2, 4, and 3. And so the least common multiple of these numbers is 12. So we're going to multiply both sides by 12. Each term is going to be multiplied by 12. And then we're going to simplify that. That just becomes this. Then once we have this, we can subtract 4x from both sides. We can subtract 15 from both sides. And then divide by 2 to get x by itself. X equals 3 halves. Here's another practice question. Pause the video, then we'll talk about this. Okay. So now we're going to start by multiplying by the least common multiple, which is 6. Everything gets multiplied by 6. When we simplify all this, we're left with 3x plus 10 equals 8x plus 6. Subtract 3x from both sides. Subtract 6 from both sides, and divide both sides by 5. So notice so far, we've been solving equations. We've been talking about how to solve equations. Now, we're going to go back to expressions for a moment. Another fraction-related skill you may need on the test is simplifying a complex fraction. Complex fraction is a big fraction with smaller fractions nested in its numerator and denominator. So for example, that is a complex fraction. To simplify a complex fraction, we use a strategy remarkably similar to the one that we use for equations. Just as we can multiply both sides of an equation by the same number, so we can multiply the numerator and denominator of a fraction by the same number. To simplify a complex fraction, we multiply the numerator and the denominator of the big fraction by the least common multiple of all the denominators of all the little fractions. So for example, here's our complex fraction, and we want to clear the fractions. We want to simplify this. So the LCM, the least common multiple of the little denominators, is 12. So the little denominators are 2, 4, 3, and 2. The least common multiple is 12. So we're going to multiply the top and bottom of the fraction by 12. When we multiply through, we get 6x plus 15 divided by 4x plus 18. We can use the same technique to simplify a complex fraction composed solely of numbers, with no variables at all. So for example, if we had this, and we wanted to simplify that, well, the least common multiple of 3, 9, 3, and 2 is 18. We multiply by 18, we get 6 plus 8 over 12 plus 9. That gives us 14 over 21. We can cancel the 7's, and this equals 2/3. So that whole complex fraction at the beginning simplifies to 2/3. Here's a practice problem. Pause the video, and then we'll talk about this. Okay. So what we're going to do here is multiply by the least common multiple of 2, 6, and 7. That least common multiple is 42. So we've multiplied the numerator and denominator by 42, and I'm going to rewrite 42 this way. I'm going to rewrite it in terms of 6 times 7 or 7 times 6. And the reason I'm going to do this is that in the numerator, I'm going to keep the 6 outside, but multiply the 7 through the parenthesis. In the denominator, I'm going to keep the 7 outside and multiply the 6 through the parenthesis. And when I do that, I get this. Well, that polynomial, that quadratic in the numerator, x squared minus 10x plus 21, we can factor that to x minus 3 and x minus 7. Then the x minus 3's cancel, and we're left with 6/7 times x minus 7. In summary, we can undo multiplication by a fraction by multiplying by the fraction's reciprocal. When we have multiple fractions added or subtracted, we can clear the fractions by multiplying the least common multiple of the denominators. We multiply that on both sides. And we can simplify a complex fraction by multiplying the numerator and denominator of the big fraction by the least common multiple of all the denominators of the little fractions. Quadratic equations. You may remember quadratics from our discussion of expressions and factoring. A quadratic equation is one of the form ax squared plus bx plus c equals 0. In other words, a quadratic expression set equal to 0. Most often, these equations have two different solutions. So before we even begin to talk about how to solve these, let me say that the strategy that we learn for linear equations, try to get all the x's on one side of the equation, all the constants on the other side of the equation, that is exactly the strategy you want to follow for linear equations, but following that for quadratics is an unmitigated disaster. So do not follow the same strategy when we're dealing with quadratics. There's a completely different procedure of equation solving that we follow, and that's what we're going to talk about here. The vast majority of quadratic equations you will see on the test will have two solutions, and the quadratic coefficient, the coefficient of x squared, will equal 1, unless a numerical greatest common factor can be factored out from all three terms. The vast majority of quadratic equations you will see on the test can be solved by the factoring methods we discussed in the factoring lessons. So if you haven't seen those lessons, it will be very helpful to watch those before watching this video, because we're going to employ all those factoring strategies here. We will factor a quadratic to a product of linear binomials. And notice we'll be doing this so that this product equals 0. So very important to get things equal to 0 first, then do this factoring. Because once we have a product that equals 0, we can apply this mathematical law, the zero product property. The zero product property says if a times b equals 0, if a product of two things equals 0, then either one is 0 or the other is 0. And before we go on, let's think about this statement for a minute. Keep in mind that the or that appears in that statement is the mathematical or, not the or of colloquial language. Well, what's the distinction I'm drawing here? The mathematical or is an inclusive or. That is, it includes the and case. Thus, A equals 0 or B equals 0 includes three cases. It could be that A equals 0 and B doesn't. It could be that B equals 0 and A doesn't. Or it could be that they both equal 0 at the same time. You see, sometimes in colloquial language, people use the word or to mean the exclusive or. They mean you could do this or that, and the implication is that you can't do both. That's the exclusive or. That is not how the word or is used in mathematics. The word used in mathematics is the inclusive or, which includes the and case. And this is important here, and it will become important again in the probability lessons. Okay, now we're ready to solve. So the first thing we're going to do is factor. And we can do that from our factoring lessons. Now we're going to apply the zero product property. So if we're multiplying two things to get 0, it means either one equals 0 or the other equals 0. Now we have two mini equations. We solve them in parallel, and we get that x equals negative 12 or x equals 2. And those are the two solutions to that original equation. Here's another example. Now before we can apply the zero product property, we have to have something that equals 0. So our first step is going to be to get the quadratic equal to 0. And we're going to do this by subtracting 11 from both sides. So we get x squared minus 3x minus 54 equals 0. So 54, that's a tricky number. But notice 6 times 9 is 54. So if we have a positive 6 and a negative 9, those will add to negative 3. Those are the numbers we need. Then we apply the zero product property, set each one of those equal to 0, and solve. Again, notice that I'm being very careful to write the word or at each step. Again, the word or is not decoration. The word or is a valid piece of mathematical equipment here. Suppose we have to solve this. This looks a little bit trickier. Well, we'll start by subtracting 13 from both sides. And now notice we have a greatest common factor of 5. So we could factor that out. In fact, what we can just do is divide both sides by 5, because of course dividing 0 by 5 is just 0. So we divide by the greatest common factor. Then we get down to something like this. This is something we can factor. Zero product property, and solve for the individual roots. And those are the answers. Suppose we have this. Now we have a quadratic equaling a quadratic. Looks very tricky. And of course the test loves to throw stuff like this at you. But all you have to do is just get everything on one side. So we're going to subtract the x squared, subtract the 10x, and subtract the 16. And this will get us down to x squared minus 6x plus 9 equals 0. And notice that's a special pattern. That is the square of a difference. So we can write that immediately as x minus 3 times x minus 3. It means that our only possibility for getting 0 is if x minus 3 equals 0, or in other words, if x equals 3. So this is an example of a quadratic that has one solution instead of two. Now this one, that's tricky. If we move the 5 to the other side of the equation, we see a problem. There's no way that we can square something and get a negative number. We square positive, we get a positive number. We square 0, we get 0. We square negative, we get a positive. But there's nothing we can square to get a negative. This is impossible. This is a simple example of a quadratic that has no solutions. So as I said at the beginning, most quadratics have two solutions, but there's some that have one, and then there's some that have none. And this is a simple example of a quadratic with no solution. For the vast majority of quadratics on the test, you will follow this procedure. First of all, you will get everything on one side of the equation set equal to 0. Then you will divide off any greatest common factor. You will factor it into a product of linear binomials, and then use the zero product property to create two linear equations and solve each one of them separately. So this is the procedure. Here are some practice problems. Pause the video and solve these on your own, and then we'll talk about these. And these are the solutions. That covers most of what you need to know about quadratics for the test. On very advanced portions of the quantitative section, you may need to know and use the quadratic formula. We will cover that in a lesson in the Powers and Roots module. So don't worry about that now. We'll get to that later. To solve most quadratic equations on the test, first of all, you need to gather all terms on one side set equal to 0, then divide by any numerical greatest common factor, then factor into a product of two linear binomials, and use the zero product property to separate into two linear equations and solve. Two equations with two variables. So far, in the study of algebraic equations, we have looked at solving single equations with only one variable. For example, something like 2x plus 7 equals 15. What happens if there is more than one variable in an equation? Suppose we had something like 2x plus 3y equals 15. Now, what would it mean for someone to come and tell us, solve this equation? How would we find values that work in this equation? Well, certainly one possible value, if x equals 0, then y could equals 5, so that would be a solution. Others would be if x equals 3 and y equals 3, x equals 6 and y equals 1. Those are also values that make it work. Of course, there's no restriction that either variable has to be positive, so other solutions include x equals 9, y equals negative 1, or x equals negative 3 and y equals positive 7. And as you can imagine, we could make x more and more negative and make y more and more positive, or vice versa, so we could get quite a few solutions of that sort. Also, there's no restriction that the variables must be integers. So other solutions include things like x equals 7.5, y equals 0, or x equals 4, and y equals 2 1/3. So just on this page, notice we have 1, 2, 3, 4, 5, 6, 7 solutions for this. And it's certainly clear we could get many, many more. In fact, one equation with two variables typically would have an infinite number of solutions. Notice all those solutions, if plotted on an xy graph, would lie on a straight line. So all the 7 solutions that we mentioned, those are the 7 dots on this diagram, and they all lie on a straight line. Now, for reasons we will discuss later in the coordinate geometry module, any single equation with just x and y, neither variable raised to a power or in a fraction, can be represented by a line in the xy plane. So right now, you don't need to worry about graphing those. You don't need to worry about how would you find the slope of the line or any of that. All you need to do is just have that idea, just that association that an equation with x and y is represented by a line. That's all you need to know for this discussion here. So the first big idea is no one can ask you to solve a single equation with two variables because it would have an infinite number solution. A line passes through an infinite number of points, and every single one of those points is a solution. So there's no way anyone could legitimately ask you to solve because they'd be asking you to solve for an infinity of things all at once. Now suppose we have two equations, each with two variables. This is called a system of equation. The values of x and y must satisfy both equations simultaneously. Well, this is interesting. If each equation is a line, then it makes sense that the unique point where those two lines intersect would be the single point that satisfies both equations. So if you pick one random line and pick another random line, chances are very good that they're going to intersect somewhere. And they intersect at one point, and that one point would be the solution. So algebraically, when we're finding that solution, what we're doing is we're finding the point geometrically where they intersect. So big idea number 2 is if we have a system of two equations with two unknowns, we generally can solve for unique values of x and y. How do we solve a system of equations for these values? There are two strategies. One is substitution, and the other is called either elimination. Some sources also call it linear combination. I'll be calling them substitution and elimination. The goal of both of these methods is to reduce the two equations, two unknown situation to a one equation, one unknown situation, which is one in which we already know how to find the solution. So what we're doing, and this is often true of mathematics, we're turning a problem we don't know how to solve into a problem we do know how to solve. That's very typical for mathematics. So the substitution method. In this method, we will first solve one equation, either one, for one of the variables. In this equation, we'll get one variable by itself on one side of the equation. So those two equations I gave a moment ago, one of the equations was x plus 2y equals 11. And that's an equation where it's particularly easy to get x by itself. All I'm going to do is subtract 2y from both sides, and I get x equals 11 minus 2y. So hold on to that for a second. X equals 11 minus 2y. Now let's look at the other equation. We can replace the x in the other equation with the expression that x equals. Because x equals 11 minus 2y, it means that wherever there is an x, we can remove the x and replace it by the thing that it equals. So here's the other equation, and we're just going to write the same equation again, but we're going to replace that x with 11 minus 2y. Well, now we have a single equation with y. So now we just use our ordinary solving. We'll distribute. We'll combine the like terms. We'll subtract the 22 from both sides. We get negative y equals negative 7. Multiply by negative 1. We get y equals 7. So now we have solved for one of the two values. We solved for y. We still have to solve for x. Now we plug this value of y back into the equation that was solved for x. So we had x equals 11 minus 2y. Well, now we know that y equals 7. So we'll just plug that in. 11 minus 14 is negative 3. And so that point, x equals -3, y equals +7, that is the solution. Notice that the substitution method is most useful when, in one of the two equations, the coefficients of one of the variables equals +1 or -1. If all coefficients of x and y in the two equations are unequal to positive or -1, then solving for any variable will create fractions, which makes the solution more cumbersome. So for example, suppose we have this as our system. Suppose we try to solve the first equation for x. Okay, well, we can subtract 5y from both sides, then we divide by 4. All right, well, immediately we get into fractions. So this would not be fun to substitute. Yes, mathematically, we could solve the equation this way. We'd have to wade through a bunch of fractions, but we'd prefer not to have to do it. In systems in which substitution is not convenient, we will use elimination. We will cover the elimination method in the next lesson. In summary, a system of equations, two equations with two variables, typically has a single unique solution. And again, this would be where the two lines are intersecting. That's the point that we're finding. We can solve with either substitution or elimination. Substitution works best when one of the variables has a coefficient of plus or minus 1. And again, in the next lesson, we'll talk about elimination. In the previous lesson, we discussed solving systems equation by substitution. And in that discussion, we noted that substitution, in a way, is kind of a limited value. In other words, if one of the coefficients is +1 or -1, then it's very easy to substitute. But the general case, of course, will be we'll have two equations and we'll have 4 coefficients, 2 for x and 2 for y, and none of them will equal +1 or -1. And so we try to solve with substitution. In that case, we're going to be introducing fractions into the equation. We're going to make things unnecessarily hard. Again, substitution would work. If you like to fight your way through fractions, you could find the answer that way. But I think you'll find that this method, the second method we're going to discuss, is much easier. In this lesson, we will discuss this method, elimination. So the elimination method. First, an easy example. Pause the video and think about how you would solve this, and then we'll talk about it. Okay. Notice, we are always allowed to add two equations. We can add an equation to an equation. That's perfectly allowed. Notice that we added these two equations. The +3y and the -3y would cancel. We would eliminate the 3y's. So this is a very easy example. We're going to add these two equations. When we add, 7x plus 2x gives us 9x. +3y plus -3y cancels. That gives us 0. And 5 plus 13 gives us 18. So the sum of those two equations is the equation 9x equals 18. Well, that's very easy to solve. Divide by 9, I get x equals 2. Now we can plug that value into either equation and solve for y. Let's plug it into the second equation. It looks a little friendlier. Plug in x equals 2, so we get 4 minus 3y equals 13. Subtract 4, divide by -3, and we get y equals -3. And so x equals +2, y equals -3 is the solution to that system. That example was particularly easy because in the system as given, the coefficients of the same variable were equal and opposite in the two equations. So really that was almost handed to us on a silver platter, that it was so convenient. Ordinarily, it will not be the case, but we can make it the case. The strategy is to multiply both sides of one equation by one number and both sides of the other equation by another number, so that for one of the variables, the two coefficients are equal and opposite, so that when we add, they will cancel and you will eliminate that variable. Let's look at the system we solved in the previous lesson. So this is a system we solved with substitution, and it works well for substitution because we have that one variable, x, just with a coefficient of 1. we're going to solve this same system now with elimination. And we're going to solve it in two different ways. So suppose, first of all, we want to eliminate x. So the very first step in elimination is we have to choose the variable we want to eliminate. If we want to eliminate x, what that means is, a very convenient way to do that, would be to multiply the second equation by -2. So every single part of that second equation gets multiplied by -2. Then we'll add the two equations. The -2x, the positive 2x will cancel. We'll get -y equals -7. Multiplied by -1, we get y equals 7. Then we could plug in and solve for x. So that is one way to solve using the elimination method. We could start with those same equations, and instead of eliminating x, we could also make the choice to eliminate y, and that would be perfectly valid. If we want to eliminate y, then we could multiply the first equation by -2 and the second equation by +3. And the goal is to get the y's to have equal and opposite coefficients. So if I multiply the first one by -2 and the second by +3, then I get a -6y in one equation and a +6y in the other equation. That means that when I add them, they will cancel. I'll solve for x equals -3, and then I can plug in and find the value of y. With the elimination method, we begin by choosing which variable to eliminate. And in general, we could eliminate either one. If the two coefficients of one variable are the same, or if one is a multiple of the other, then that variable is the better choice to eliminate. So sometimes we get that. So for example here, I'm going to say pause the video and decide which route you would take to solve this with elimination, and then we'll talk about it. Okay, well notice that the coefficients of y, +2 and -4, one is a multiple of the other. So that would be the better choice. It would not make sense to eliminate x here. It would be much more strategic to eliminate y, because all we'd have to do is multiply that top equation by 2. Multiply the top equation, every term, by 2. Then we have a +4y and -4y. We add, those cancel. We get 10x equals 80. X equals 8. Then we can plug that into the first equation. We can actually plug it into either one. It doesn't matter. Plug it into the first equation. We get 2y equals 3, or y equals 3/2. So x equals 8, y equals 3/2 is the solution to that. Here's another practice problem. This is a system that we had in the last lesson. Remember, at the end of the last lesson, we had a system, and we said substitution really didn't work very well for this, so we didn't solve it. So here it is again. Now we're going to solve it with elimination. And in fact, I'm going to say pause the video and try on your own to solve this with elimination. Okay, well, let's talk about this. I'm going to choose to eliminate y. We could do either way, but I'm going to choose to eliminate y. I'm going to multiply the first equation by +2 and the second equation by -5. And what I'm trying to do is get to +10y and -10y. So when I do those multiplications, these are the equations I get. I multiply every term in each equation. Then I add the two equations. I get -17x equals -68. Well, here it's good to know that 68 is 17 times 4. So when we divide -68 by -17, we get +4. Now I can plug that into either equation. I'll plug it into the first equation and get 16 plus 5y equals 1. Subtract 16 from both sides, 5y equals -15, y equals -3. And so the solution to that system is very simply x equals +4, y equals -3. Here's another practice problem. Pause the video and then we'll talk about this. This is a tricky practice problem because this is a practice problem where it would be very easy to make the work for yourself 100 times more difficult than it has to be. As a general rule, if the test gives you a system and asks you to solve for the value of the expression, you do not need to solve for the values of the individual variables. There will always be an elegant shortcut that leads directly to the value of the expression. Notice here that the coefficient of x is 3 bigger in the second equation than it is in the first equation than in the second equation. 5x, 5 is 3 bigger than 2. And notice that the coefficient of y, 2, is also 3 bigger than the coefficient in the other equation because positive 2 is 3 bigger than negative 1. Well, that's very interesting. So that's a suggestion right there that we should subtract the equations. So I'm going to multiply the second equation by a negative 1 and then just add them. So when I do that, lo and behold, I get 3x plus 3y equals 36. I divide by 3 and I get x plus y equals 12. And that is the answer because the question was asking for the value of x plus y. Elimination is the more convenient of the two if the two coefficients of the same variable are equal or opposite, or one is a multiple of the other. So certainly if we see that, that makes elimination easier, but in a general case, elimination is always easier than substitution. If you are asked to find the value of an expression, you will almost always be able to find that without finding the values of the individual variables. And in that last problem, it would have been a mistake to solve individually for the value of x and the value of y. All we needed was x plus y.